Let's look at another example just to continue to practice our optimization skills. Suppose that an airline policy states that all baggage must be box-shaped with a sum of length, width, and height not exceeding 64 inches. What are the dimensions and volume of a square-based box with the greatest volume under these conditions? So we have this airline policy that's oddly restrictive in what sort of luggage you can take. You have a box shape, so we're going to draw a box shape with a square-based box. So this one's going to be perhaps a little bit tricky to draw. Oops. But we should have a square base, so we might want to draw something like that. I think that turned out pretty good, all things considered. So when I say a square base, what I'm really talking about is you can either think about that as the bottom or the top. I think it's easiest to think about it as the bottom. Square base means that this side right here should be the same length as this side right here. I'm going to give these variable names. How about x and x? We don't have any restrictions on this dimension here, though, on my height, so how about I call that y? So I've taken all of the information that this problem has given me. I've drawn just an absolutely lovely picture. And now I need to think about what is my objective function. That's going to be my first step here. So what am I trying to do? I want to find the greatest volume. So I'm trying to maximize here. I want to maximize my volume. Well, how do I find the volume of a box? I know that the volume of a box is just length times width times height. So here in this case, the length is x, the width is also x, times the height is y, so v equals x squared y. This is the function that I'm trying to optimize. So we can say you're either trying to maximize this, or maybe we'll label this as your objective function. In either case, we have our objective function. This is what we're going to be working with. But of course, I can't work with only this function because I have these two variables. I have a function of both x and y. This is a little bit more complicated. We would like to simplify this somehow. So I'm going to come up with a constraint. I'm going to look, well, what other relationships do x and y share? What are the limitations placed on this problem? Well, our oddly restrictive airline policy says that the box-shaped baggage must have a sum of length, width, and height not exceeding 64 inches. So if I take the length plus the width plus the height, it must not be greater than 64. So let's just say equal to 64. If we want to maximize the volume, we probably want to use as large of dimensions as we can. So we said the length and the width, those are both x right here. So x plus x, my height in this case is y, is equal to 64. So 2x plus y equals 64. This is a constraint that I have. So this is a constraint. I'd really like to use this constraint to simplify my objective function. So I'm going to take it very briefly, solve it for y. So y is equal to 64 minus 2x. Here's my constraint. And I'm going to plug that into my objective function for y. I'm going to substitute this in. So I'm going to try to maximize v equals x squared times y. Y we said was 64 minus 2x. V is equal to 64x squared minus 2x to the third power. So okay, that's pretty cool here. What else do I want to do then? Well, I know what I'm trying to do. I'm trying to maximize this function. I'd like to be able to say on this interval, but I need to figure out what my interval of interest is. So I need to figure out my interval of interest, aka my domain. And for your domain, for determining this interval of interest, look back at your picture, look back at the variables that you're using, and ask yourself what makes sense for those variables. Well, x is a dimension. Doesn't make sense if x is negative. So on the one hand, I'm going to say, well, x should be greater than or equal to 0. You could make the argument here that x should just be strictly greater than 0. I think it makes the problem a little bit easier if you say greater than or equal to, but you could actually do this problem either way. So x is greater than or equal to 0. Well, what's the other variable that I have? I have y. Y also represents a dimension, so y should also be greater than or equal to 0. But this isn't terribly helpful because now we have something, I have x and y. I just want x because my function is only in terms of x. So I'm going to plug in my constraint that I found earlier in for y. I'll say 64 minus 2x should be greater than or equal to 0. We can solve this for x pretty quickly here. Negative 2x is greater than or equal to negative 64. So x is less than or equal to 32. So here, I've said two things. I've said x should be greater than or equal to 0, so x should be bigger than 0. And x should be less than or equal to 32. It should be smaller than 32. In other words, it should be between 0 and 32. So I'm trying to maximize this function. So I want to maximize this function on the interval 0 to 32. And I see now that this is a closed interval. I know exactly what I want to do. I want to find my critical points. Once I have those, I'm going to test my critical points and the two endpoints of this interval in my original function, to my volume function, and then just pick the highest one since we're trying to maximize here. So, all right, let's work with this. Let's start by finding our critical numbers. So let's say v prime, I need my derivative first of all. That'll be 128x minus 6x squared. I want to set this equal to 0. I know it's a polynomial. The only critical numbers are going to come from horizontal tangent lines. So 128x minus 6x squared equals 0. I will factor out, let's see, 2x from each one. That will leave me with 64 minus 3x is equal to 0. And then I can take each factor, set it equal to 0. So 2x is equal to 0. Gives me x equals 0. Well, I was going to test this one anyway because it was the end point of one of my intervals. So that's not a super helpful critical point. The other one, 64 minus 3x is equal to 0. I will have negative 3x is equal to negative 64. Gives me x equals 64 over 3. I'm just going to leave it as a fraction for now, I think. So I am going to take x equals 64 over 3 along with the endpoints of my interval, which are 0 and 32, and plug those into my volume function to see which one gives me the largest possible volume. And actually, one thing I should check before I do that, one thing I want to just talk about very briefly, 64 over 3, you'll want to make sure that those critical points fall in this interval. You'll want to make sure that 64 over 3 falls between 0 and 32. If I look at 64 over 3, here this is approximately equal to 21.3 repeating, so that's definitely between 0 and 32. So this it falls in our interval. That means we get to continue to think about it. If we had ended up with, say, x equals 40, we wouldn't even consider that critical point. We would only be looking at the endpoints in that case. So I'm going to take these 3 points, 1, 2, 3, plug those into my volume function, and then just figure out what's going to give me the maximum possible volume. So let's see, V equals, let's start with actually 0. Let's say V of 0 is equal to 64 times 0 squared minus 2 times 0 to the third power. Well, that's just going to give me 0. Not a very large box. Let's start with 32 then. Oops. So let's see, I have 64 times 32 squared minus 2 times 32 raised to the third power. And here I'll probably need my graphing calculator just to help me out here. Minus 2 times 32 raised to the third. Here that's not very interesting. I ended up with 0 again. And then I'll do the same thing one more time with my critical point, which is either 64 over 3 or 21.3 repeating. So 64 times 64 over 3 quantity squared minus 2 times 64 over 3 raised to the third power. Just has to be bigger than 0. Not a tremendously high bar here to beat. So let me type this into my graphing calculator very quickly. And I should have roughly, as a decimal approximation, because the number's not going to be super nice to work with, here I end up with roughly 9,709.04 inches. Well, and I should say cubic inches since we're working with volume. This is definitely way bigger than 0. So this seems like the best possible choice. So one thing I want to just check really quickly, I want to look back at my problem and just make sure that I answered everything. It says, what are the dimensions? Okay, well, let's just start there. What are the dimensions? The dimensions, we have x, right? This is x equals 21.3 repeating. So x equals 64 over 3 inches. The other part of the base would be x equals 64 over 3 inches. The height, y, well, I need to go back and look at my constraint function there. So y, we said, was 64 minus 2 times x. So I can just say 64 minus 2 times 64 over 3. So 64 minus 2 times 64 over 3, that gives me, well, 21.3 repeating again, or, well, 64 over 3 inches. So those are the dimensions. I have x, I have x, I have y. What else did I want to know? So what are the dimensions and volume? So what's the volume? And I could do a couple things here. I could just take 64 over 3 times 64 over 3 times 64 over 3 and calculate the volume. But I actually already looked at the volume. It's this 9,709.04 inches cubed. This is our maximum volume. So maybe I'll just restate that. The volume here is 9,709.04 cubic inches if we want to talk about the maximum volume. So here's the maximum volume, and then these are the dimensions that will give us that maximum volume.